Today we're going to be talking about section 1.9, the matrix of a linear transformation. So in the last video, we talked about linear transformations, and we talked about how every matrix transformation, so a transformation that can be written as a matrix times a vector, every matrix transformation is a linear transformation. In fact, it's also true the other way around. So that's what we're going to be focusing on today. Every single linear transformation out there can be written as a matrix transformation. So another way of saying that is that every single linear transformation, if T is linear, then there exists some matrix A so that we can encode our transformation in this matrix multiplication. So the first part of what we're going to be doing today is trying to find what that matrix is. So the way that we're going to do this is we're going to use the last thing that we talked about in our last video on section 1.8. So recall that if you have a linear combination, if you take the transformation of that linear combination, you could also take the transformation of the individual vectors first and then combine them afterwards. We're going to take advantage of this. The second thing we're going to need as we're trying to find our matrix that encodes a transformation is a new definition. So EI is called the standard basis vector, and it's going to be the ith column of the identity matrix. So this is going to depend on obviously what dimension we're living in. So let's say we're living in R3. Then we'll have three standard basis vectors. The first one will be I1. It will be the first column of the identity matrix. So it'll look like this. The second one, I2, will be the second column of the identity matrix with a 1 in the second spot, and E3 will be the third column of the identity matrix with the 1 in the third spot. So these are our standard basis vectors. We'll talk a lot more about them later on in the term, but for right now, we're going to use them specifically to find our matrix that encodes our linear transformation. All right. Let's take a look at how this works in an example first. So let's say we're going to live in two dimensions. So we'll have E1 equaling to 1, 0, and E2 equaling to 0, 1. And let's say we have a transformation and we don't know what it does to every vector, but let's suppose that we know what it does to our two basis vectors. So let's say it sends E1 to 1, 2, 3, and it sends E2 to 4, 5, 6. So again, I don't know what my transformation does. I just know that it's linear and where it sends these two vectors. So let's see if we can figure out where it sends an arbitrary vector x. So again, we're living in two dimensions here, or our domain is. So x is going to have two components, x1 and x2. And the key that we're going to use here is that we can decompose this into a linear combination of our basis vectors. Oh, sorry, this is E2. So we can decompose this into saying that any vector x1, x2 can be written as x1 times our first basis vector plus x2 times our second. Yeah. And so just make sure that you're convinced of this. If we actually multiplied out this linear combination, we have x1 times 1 plus x2 times 0 gives us x1. That's our first spot. x1 times 0 plus x2 times 1 gives us x2, and that what goes in our second spot. So since we can break down any vector as a linear combination of our E1 and E2 in this way, we can now use that superposition principle that we talked about at the end of the last video. So we can say instead of first taking the linear combination and then transforming, we can first transform and then take the linear combination. So we can rewrite this by pulling out our x1 and x2 and first transforming our E1 and E2. And conveniently enough, we already know what these two are. So this is going to look like x1 times 1, 2, 3 plus x2 times 4, 5, 6. And this is a vector equation, but we could rewrite it as a matrix equation if we wanted to. So we've got 1, 2, 3, 4, 5, 6 times x1, x2. Okay, so x1, x2 was a completely arbitrary vector in our domain, and we were able to write it as a matrix equation. So in fact, we found our matrix A. So what did we just do? What we just did is we saw where our transform sent two specific vectors, and we're able to use that to build our rule for our transformation. So now we know where our transformation sends everything. This is insane. We took two pieces of information and are able to extrapolate where infinitely many vectors get sent. This is really, really cool. And we can do this with any linear transformation. So if we have a linear transformation, all we need to know is where it sends those basis vectors to be able to find our matrix. So this is encapsulated right here. So let T be a linear transformation that goes from Rn to Rm. And A is going to be the m by n matrix where the first column of A is where T sends the first standard basis vector. So this is an entire column here. The second column of A is where T sends the second standard basis vector, all the way up to the nth column of A being where T sends the nth standard basis vector. Yeah. Cool. So this matrix is going to encode our entire linear transformation. So A is going to be the unique matrix such that our transformation is encoded by this matrix transformation for all x in in Rn. And A is called the standard matrix for T. All right. Let's look at an example of how this might be useful in real life. So let's say that you have maybe a typesetting program and you want to be able to italicize. So you want to send, let's say, the letter N to an italicized version, of N. Pretend that looks a little bit better than it does. Okay, so let's say we see sort of these points here at the bottom of N maybe stay the same, and these points up at the top of N, we want them to sort of get shifted over. All right, so I want to know how to encode that transformation so that I can feed it into my computer and have it be able to apply this to any point I might want. Well, as we see in our theorem up here, the only thing we actually need to know is where it sends the basis vectors. So this is in two-dimensional space. So we just need to know where this transformation, this italicization transformation, is going to send each of our basis vectors. So let's take a look. If we look at 1, 0, that is going to be on a 1 on the x-axis and a 0 on the y. As we saw here, we're keeping our sort of baseline exactly the same. So this is going to get sent totally to the same place. Now, where do we want to send 0, 1? Let's say 0, 1 is, well, it's going to be up on the y-axis. Let's say it's this point here. Well, the y part of it stays the same, but we're shifting the x part over. And this is rather an extreme italicization. That looks like maybe we're shifting the x over to almost over to 1, and then our y stays exactly the same. So we can use these together to build the standard matrix for T and just fill in those columns for our standard matrix. And we can use this to now italicize in the same very extreme way any point and any shape we might want. This is used very, very frequently in computer graphics. So that is sort of our key application right here. If you want to see more examples of matrices that do things to certain geometric shapes, there's lots more examples in the book in section 1.9. And if you want more information on computer graphics, there's more information in section 2.7. Okay. So we now know how to find our standard matrix for a linear transformation. Any linear transformation can be encoded as matrix multiplication, and this is how we find that matrix for it. All right, so for the next thing I wanted to talk about is thinking of T, our transformation T, as a function. So for those of you who have talked about functions before in various classes, you know that they come in a couple of flavors. One type of function is an onto function. So a mapping, or so a function, or in this case, a mapping, a linear transformation that goes from Rn to Rm is going to be called onto if every single vector b in Rm is the image of at least one x in Rn. What do I mean by this? I mean that our range is our codomain. So basically, if I have a function, let's say this is our domain, and this is our codomain over here. A function is onto if, let's maybe give ourselves one less point in the codomain. Our function is onto if every single thing in the codomain gets hit. So we see that with this particular function, every single point in our codomain is hit. In this case, our codomain is an infinite space, so our statement is just that our range would be the entirety of Rm. There's another type of function that you maybe have heard of before, which is called a one-to-one function. Our linear transformation equivalent of a one-to-one function is that a mapping T that again goes from Rn to Rm is going to be one-to-one if every single b in the range is hit by only one x from the domain. So what this means is if we have our domain, and maybe here's our codomain, everything that gets hit in the codomain only gets hit by one thing. So for instance, this up here is onto, but it's not one-to-one because this point has two arrows pointing at it. Down here, this is one-to-one, but it's not onto because we have this point right here in the codomain that's not getting hit, that's not in the range. Okay, so this is what it means to be one-to-one and what it means to be onto. Now, given these definitions, we have some very easy ways to tell if our transformations are one-to-one and onto. So our first one is if we have a linear transformation and we know it's linear, then our transformation is going to be, oops, sorry, there you go. Our transformation is going to be one-to-one if and only if t of x equals 0 has only the trivial solution. So again, we're going from Rn to Rm, it's linear, and it's one-to-one if and only if when we plug in 0 is only getting hit by 0, it's not getting hit by anything else. So this actually makes quite a bit of sense, right? Because we know from our study of homogeneous systems in section 1.5 that if we have a homogeneous system, this always has the trivial solution. If it has a non-trivial solution, that would mean 0 would get hit by infinitely many points by our transformation. That's clearly not one-to-one. So we're trying to say if it's one-to-one, it should only get hit by the trivial solution. Also in section 1.5, we talked about non-homogeneous systems and how the solutions to non-homogeneous systems are just translations of the solutions to the homogeneous ones. So that means that if the homogeneous system only has the trivial solution, then every non-homogeneous system has a unique solution, which is just the definition of one-to-one. Now, we can turn this into something a little bit more useful by using our vocabulary from section 1.7 when we were talking about linear independence. So let's take our linear transformation, then we can say two things about it. First of all, again, this is going from Rn to Rm. This is Rn, it takes our domain and it maps it onto our codomain if and only if the columns of A span Rm. And then T is going to be 1 to 1 if and only if the columns of A are linearly independent. The second one is very easy to see directly from what we just said, right? So we just said it's 1 to 1 if and only if there's only the trivial solution to the homogeneous system. That's literally the same thing as saying the columns are linearly independent. On the other hand, T maps Rn onto Rm if and only if the columns span Rm. The columns of A spanning Rm means every single thing in Rm can be a linear combination of the columns of A. That's the same thing as saying everything in Rm gets hit by this transformation, which is the same thing as saying the transformation is onto. So here are two really easy things to check. We already know how to check them from the last few weeks to be able to tell if a transformation is onto or 1 to 1. Let's take a look at a very quick example. Let's say we have a linear transformation whose standard matrix is 3, 5, 1, 1, 7, 3. And we want to know this linear transformation is going to go from R2 to R3, and we want to know, is this 1 to 1 and is this onto? It's defined by this matrix multiplication. Is it 1 to 1? Well, it's 1 to 1 if and only if the columns are linearly independent. Let's take a look at these columns. There are only 2 of them, and they are not scalar multiples of each other, so they are linearly independent. So this is 1 to 1. Is it onto? Well, it's going to be onto if and only if the columns span Rm. If we take a look at this, there is no way for the columns to span Rm. That's because there are more columns than there are rows. So if we collapse this down into its reduced row echelon form, the best we can hope for the reduced row echelon form gives us a row of zeros at the bottom. That means that we are requiring whatever's down here to be 0 to ultimately have a satisfactory, consistent system. That means that not any, there are restrictions on what we can get out in our image, so this is not onto. All right, there you have it. We have talked about how linear transformations always can be encapsulated by matrix multiplication. We talked about how to find that standard matrix, and we talked about 1 to 1 and onto functions and how to tell if a function is 1 to 1 or onto. That is all I have for you today. I will see you all in class.